Welcome to today's comprehensive tutorial on Python loops. Whether you're studying for an exam, working on assignments, or preparing for technical interviews, mastering these fundamental concepts is essential. This presentation focuses on how Python handles repetition through loop structures like while loops and for loops. These loops are foundational to programming because they allow us to automate repeated tasks, process collections of data, and build logic that responds to dynamic conditions. These topics not only build fluency with core Python syntax, but also prepare you to write more readable and maintainable code in real-world applications. Mastering Python loops, from while to for and beyond by the programming professor. The outline for this presentation follows a logical progression, starting with a general introduction to the concept of loops. From there, we'll examine the while loop in detail, followed by the for loop and a comparison of when each should be used. We'll then look at nested loops, which involve placing one loop inside another, a common pattern for working with grid-like data or generating combinations. Next, we'll discuss incremental program development, which emphasizes building loops gradually and testing as you go. After that, we'll shift focus to loop control mechanisms, including the break and continue statements, which alter the normal flow of a loop. We'll conclude with the enumerate function, which provides a cleaner and more Pythonic way to access both the index and the value during iteration. This structure ensures that we cover not only the mechanics of loops, but also best practices for using them effectively. At its most basic level, a loop is a control structure that repeatedly executes a block of code, called the loop body, as long as a condition remains true. Before each repetition, the condition is checked. If it's true, the loop body runs. If it's false, the loop ends. Each execution of the loop body is called an iteration. This structure is essential for automating tasks that would otherwise require repetitive manual code. The diagram on this slide illustrates the loop logic. Start with a condition check, execute the loop body if the condition holds, then recheck the condition to decide whether to continue. This basic model applies to both while and for loops, though the mechanism for managing the condition differs slightly between the two. Understanding this control flow is crucial, as it lays the groundwork for more complex operations involving collections, user input, and cumulative calculations. A classic use of a loop is calculating the average of a list of numbers. This task involves summing all the values and keeping track of how many values there are. The slide outlines the process step by step. You begin by initializing a variable to hold the total sum and another to count the number of values. Then, for each number in the list, you add it to the total and increment the count. After the loop completes, you calculate the average by dividing the total by the count, and then output the result. This structure reinforces the use of accumulators and counters inside loop bodies, which are standard tools in algorithm design. The accompanying flowchart mirrors this logic and makes the iteration process easy to follow. Start with setup, check for more numbers, update totals, and compute the result after the loop ends. Another common use of loops is counting the number of elements in a list that meet a specific condition. In this example, the goal is to count how many values in a list are negative. The structure follows a familiar pattern. Initialize a counter to 0, iterate through the list, check whether each value is negative, and increment the counter when it is. At the end of the loop, the counter holds the final result. This is a great example of the element-by-element processing mindset that loops enable. Rather than applying a complex operation all at once, loops allow you to isolate each value, evaluate it, and decide what to do. This technique is applicable to a wide range of problems, from filtering data to validating user input or even identifying patterns in large datasets. This final example in the set demonstrates how a loop can be used to determine the maximum value in a list of positive numbers. The program begins by initializing a variable, maxval, to a baseline value, in this case -1. Then, for each number in the list, the program compares it to the current value of maxval. If the new number is larger, it becomes the new maxval. By the time the loop finishes, maxval holds the highest number encountered in the list. This is another classic pattern in programming, updating a variable based on some condition during iteration. It's particularly useful in scenarios where you're scanning for extremes, maximums, minimums, or first matches. Like the previous examples, it emphasizes the power of processing one item at a time and updating a cumulative result as you go. The while loop is one of the two main looping structures in Python. It repeats a block of code as long as a specified condition evaluates to true. That condition is checked before every iteration, so if the condition is false from the beginning, the loop body is never executed. This makes while loops ideal for cases where you don't know in advance how many times a loop should run. A common example is a guessing game, where the program keeps prompting the user until they guess correctly. The key to using while loops effectively is ensuring the condition eventually becomes false. Otherwise, you'll end up with an infinite loop. This is usually handled by updating a variable inside the loop body, such as a counter or a user input value. That influences the loop condition. Understanding how to control the loop condition is critical for ensuring that loops not only do the right work, but also terminate correctly. A sentinel value is a special input used to signal the end of a loop. It's not part of the normal dataset, but serves as a clear indicator that it's time to stop iterating. Sentinel-controlled loops are commonly used with while loops, especially in programs that read user input or external data where the number of inputs isn't known ahead of time. For example, you might prompt users to enter names until they type the word stop. In that case, stop is the sentinel. It doesn't get processed like the other names, but instead tells the loop to exit. This approach gives the user control over the loop's duration and makes the program flexible for varying amounts of data. Sentinel values are particularly helpful in interactive scripts, file reading tasks, and any loop where the end condition depends on a meaningful signal rather than a fixed number of iterations. An infinite loop is a loop that never terminates because its condition always evaluates to true. Sometimes this is intentional. For instance, in real-time systems like video games or servers that need to run continuously and check for updates or input. However, infinite loops are more often the result of a programming mistake. One common cause is failing to update the variable that controls the loop condition. Another is relying on a condition that may never evaluate to false, such as checking for exact equality in floating point values, which can lead to logical errors. To avoid unintentional infinite loops, it's best practice to ensure the loop condition changes in a predictable and finite way. This can mean using relational operators like less than or greater than instead of strict equality, and adding logging or print statements to verify that the loop is progressing as expected. Developing an instinct for spotting and preventing infinite loops is a key skill for debugging control flow in any program. Some loops are designed to process data piece by piece until a certain goal is reached. A good example of this is printing each digit of a number in reverse order. The technique involves using a while loop that continues as long as the number is greater than 0. On each iteration, the loop uses the modulo operator to extract the rightmost digit and the floor division operator, // to remove it from the number. This process repeats until there are no digits left to extract. It's a clear demonstration of how arithmetic operations and loop logic work together to manipulate structured data. This kind of loop is useful when working with numeric data at the digit level, whether you're implementing a calculator, building a number parser, or performing digital transformations. It also reinforces the principle of gradually reducing a problem through iteration. This next example applies a while loop to compute the greatest common divisor of two numbers using Euclid's algorithm. This algorithm works by repeatedly subtracting the smaller number from the larger until the two values become equal. That final value is the GCD. The logic begins by checking whether the two numbers are different. If they are, the loop continues. Inside the loop, a conditional statement determines whether to subtract num_b from num_a or the reverse. This kind of loop is ideal for situations where the number of iterations isn't known in advance, but is guaranteed to end. Eventually, the two numbers will converge. What makes this a useful teaching example is that it avoids division and uses only subtraction and conditionals to solve a classic math problem. It's also a good example of how loops, conditionals, and mathematical logic come together in algorithm design. In this example, we move from number processing loops to a more interactive, text-based scenario. The program simulates a basic conversation with the user. It uses a while loop that continues as long as the user's input is not the word goodbye. Within each loop iteration, the program selects one of three random responses using the random.rand int function. The point here isn't just about text responses. It's about showing how loops can be used in dynamic, user-facing applications where the flow of the program depends on ongoing input. This structure is common in chatbot systems, command line interfaces, and interactive forms. Each loop iteration responds to new input, and the exit condition is a specific word. This helps reinforce the utility of Sentinel-style logic, while also introducing randomness and basic user interaction, all within a controlled loop. This slide demonstrates another Sentinel-controlled loop, but this time with numeric input. The goal is to compute the average of several numbers entered by the user, with 0 serving as the Sentinel value that ends the loop. Each time a number is entered, it is added to a running total and a count is incremented. When the loop ends, the program checks whether any values were entered, and, if so, calculates and prints the average. If no values were entered, it prints a different message. This is a useful pattern when the number of inputs is unknown in advance, and it reinforces how to use a loop to handle variable length data. The inclusion of a condition to check for empty input before computing the average also demonstrates good defensive programming. It's important to ensure your logic can gracefully handle edge cases like 0 entries. Counting is one of the most fundamental tasks you can perform with a while loop. This slide explains the structure clearly. You initialize a loop variable before the loop, update it during each iteration, usually by incrementing it, and terminate the loop when the condition becomes false. Forgetting to update the loop variable is a common mistake that leads to infinite loops. The key takeaway here is that the loop variable must change in a way that guarantees the loop will eventually end. Counting loops are essential in many programming scenarios, including indexing through lists, generating repeated patterns, or keeping track of how many times something has occurred. This slide serves as a foundation for more complex variations of counting logic, which will be explored next. Building on the previous example, this slide introduces several variations on counting with a while loop. You're not limited to counting up by one. In fact, many tasks require different patterns. You might count down when you're working with timeouts or reverse iteration. You can also increment or decrement by steps larger than one, such as every second number or every fifth. In other cases, you might update the variable using multiplication or division to create exponential growth or decay. The condition can be flexible too, As long as it eventually evaluates to false, the loop remains valid. These variations allow you to tailor the loop's behavior to match the needs of your program. Understanding these different counting patterns gives you much more flexibility in loop design and makes your code more expressive and efficient. This slide introduces practical applications of counting with while loops. 3 common examples are provided: computing a factorial, generating a Fibonacci sequence, and simulating compound interest. Each of these problems uses a while loop to continue until a condition is met, such as reaching a target value or exhausting a sequence. The factorial example involves multiplying a decreasing sequence of integers, which is commonly used in combinatorics. The Fibonacci example starts with 2 initial values and builds up a sequence by summing the previous 2, a task often encountered in recursive algorithms. The interest simulation increases a balance over time based on a percentage rate. These examples highlight why while loops are preferred in situations where the number of iterations isn't known up front. They also demonstrate how loops can represent real-world processes, which makes them a powerful tool for modeling, simulation, and problem-solving. Here we transition to for loops, which are typically used to iterate over the elements of a container like a list, string, or dictionary. A for loop assigns each element of the container to a loop variable in sequence, executing the loop body for each item. This form of iteration is very common in Python because it eliminates the need to manually manage a loop variable or worry about indexing. The syntax is straightforward and concise. You define the loop variable and the container, and Python handles the rest. Once the loop finishes iterating through all the elements, execution continues with the code that follows the loop. For loops are ideal for tasks that require visiting each item in a sequence exactly once, such as processing user data, formatting output, or performing checks on a collection. In addition to lists, for loops can also iterate over other sequence types like strings and dictionaries. When iterating over a string, each loop iteration processes one character at a time. For example, iterating over the string blue results in accessing the characters B, L, U, and E sequentially. For dictionaries, iteration typically proceeds over the keys, though you can also explicitly access key-value pairs if needed. The loop variable holds each key, and you can retrieve the corresponding value using dictionary indexing. This is especially useful when you want to analyze or transform data stored in key-value structures. These examples show how for loops generalize across different types of containers, making them a flexible and powerful tool in Python programming. This slide presents several real-world use cases of for loops, including calculating total revenue, computing an average, and iterating in reverse. The first part shows how a loop can use an accumulator to sum values in a list, such as daily revenue figures. Then, the total is divided by the number of entries to find the average. The example also introduces reverse iteration using the reversed function, which is useful for tasks like displaying items in reverse order or analyzing trends in historical data. These examples go beyond simple iteration. They show how a loop can both collect and transform data. They also reinforce the importance of loop planning, thinking through what needs to happen during each iteration and what must be done after the loop ends. These patterns are commonly used in data processing, reporting, and analytics. The range function is a built-in tool that generates a sequence of integers, typically used in for loops when you want to iterate a specific number of times. This slide explains its basic forms. With one argument, range of y generates values from 0 up to, but not including y. With 2 arguments, range of x, y generates values from x to y minus 1. These sequences are especially helpful when you need to access list indices, repeat a fixed number of operations, or simulate a counting loop. Unlike using a while loop where you manually manage a counter, range simplifies this process by handling the counter and the stop condition internally. Understanding how to use range is essential for writing concise and readable counting loops in Python, especially in structured tasks like iteration over matrix rows, steps in a process, or any loop where the number of iterations is known in advance. This slide extends the range function by introducing its three-argument form, which allows for custom step sizes, including negative steps for reverse iteration. The full syntax is range of start-stop step, and it generates a sequence beginning at start, ending just before stop, and progressing by step. For example, range of 0, 50, 10 generates 0, 10, 20, 30, and 40. When the step is negative, such as in range of 3, -1, -1 the sequence counts downward, which is helpful when iterating in reverse. This form is particularly useful for generating even-numbered sequences, skipping values, or looping backward through a structure. The three-argument range gives you complete control over how a loop progresses, and understanding it is essential when building flexible loop structures that don't always follow a standard, forward-counting pattern. It's important to note that calling range doesn't produce a list. It creates a special type of object known as a range object. This object represents a sequence of numbers defined by a start, stop, and step, but it doesn't actually store the entire sequence in memory. Instead, it generates each value on the fly as needed, which makes it highly memory efficient. The range object behaves like a sequence, meaning you can iterate over it in a for loop just like a list. If you do need the full list, for instance, to access elements by index or to store them, you can convert it using list of range. However, for most looping tasks, keeping it as a range object is faster and more efficient. Understanding this distinction helps you write cleaner, more performant code, especially when working with large or complex sequences. This slide compares while loops and for loops, especially in the context of counting tasks. Both can be used to repeat an action a specific number of times, but they do so differently. A while loop requires manual setup. You have to initialize a counter variable, write a loop condition, and increment the counter inside the loop. If you forget to update the counter, you risk creating an infinite loop. In contrast, a for loop paired with range automatically handles all of that: the counter, the stopping condition, and the step size. This makes for loops cleaner and more error-resistant for tasks where the number of iterations is known in advance. While while loops offer more flexibility, for loops are generally preferred for structured counting because they are more concise and easier to read. When deciding between for and while loops, context matters. Use a for loop when the number of iterations is known ahead of time, or when you are working with a container such as a list, string, or dictionary. For example, if you need to print each element in a list or perform an operation a fixed number of times, a for loop is ideal. On the other hand, choose a while loop when the number of iterations is not known in advance, such as when waiting for a specific user input or repeating until a condition is met. These guidelines aren't strict rules, but they are reliable starting points for choosing the right loop structure. By using the appropriate loop for the task, you make your code easier to understand and reduce the likelihood of logic errors or infinite loops. Nested loops are loops placed inside other loops. The outer loop controls how many times the inner loop runs. For each iteration of the outer loop, the entire inner loop runs from start to finish. A classic use case for nested loops is generating combinations, such as creating all two-letter domain names like aa.com, ab.com, and so on. In this case, the outer loop iterates over the first letter, and the inner loop iterates over the second. Helper functions like ord and chr are used to convert characters to and from their Unicode integer values, allowing you to step through the alphabet programmatically. Nested loops are essential in problems involving matrices, coordinate grids, or exhaustive searches. They can be powerful, but also computationally expensive, so it's important to understand their structure and to use them wisely. Next, we show the implementation of the domain name example as actual Python code. The outer while loop starts at A and increments the first letter until it reaches Z. Inside it, a nested while loop resets and iterates through the second letter, also from A to Z. On each iteration, it prints a new domain name formed by concatenating the two letters and adding .com. This code emphasizes several important programming practices: looping through character sets, resetting inner loop variables, and incrementing characters using Unicode conversions. It's a practical demonstration of combining loops and string operations to generate structured output. This kind of logic can be adapted to broader applications, such as password generation, coordinate mapping, or constructing all possible pairs in a dataset. While the logic is simple, it shows how loops can build structured results from basic operations. Here we introduce the concept of incremental programming, a strategy where programs are built step by step instead of all at once. The idea is to start with a minimal version that works, then gradually add features while continuously testing. This helps isolate errors, reduces complexity at each stage, and leads to better structured code. Writing all code at once may seem faster, but it often results in harder to diagnose bugs and poor organization. Incremental programming encourages a tighter feedback loop, allowing you to confirm that each new piece of logic integrates correctly. It's especially important when building loops and conditionals, which often have interdependent behaviors. By testing frequently and making small, traceable changes, you improve reliability and maintainability. This approach reflects best practices in software development and is particularly useful in educational settings and early-stage projects. Here we see the first version of an incremental project, a phone number program. The user inputs a string that may contain letters, digits, and hyphens, such as 1555 holiday. The goal is to eventually convert any letters to their corresponding digits, based on a phone keypad. In this initial version, the focus is simply on iteration, walking through each character and printing its index and value. This lets the programmer confirm that the loop processes every element correctly. It's a textbook example of scaffolding, a method of verifying each building block before moving on to the next. By printing index character pairs, the program makes internal behavior visible, which helps with debugging and validation. This technique is foundational when processing strings or lists, as it ensures the basic loop logic is functioning before any transformation is introduced. The second version of the phone number program builds on the first by beginning the transformation process. Now, the loop checks whether each character is a digit. If it is, the character is added directly to the result. If not, a placeholder question mark is used instead. This version introduces conditional logic within the loop and starts forming the final output string. A fix me comment is included to mark where future enhancements, like converting letters, will go. This is a great example of how incremental programming lets you gradually build functionality. Rather than implementing all letter-to-digit mappings at once, this version allows the programmer to verify that digits are handled correctly and that non-digits are being marked. This practice of validating partial behavior is crucial in larger applications, where unchecked assumptions can lead to subtle bugs. It also reinforces good development habits, like using comments to plan the next steps in your implementation. In this third version of the phone number program, we begin transforming letters into actual digits based on the standard telephone keypad. Specifically, the program now converts letters A through C, both uppercase and lowercase, into the digit 2. It also improves the logic from the previous version by preserving hyphens as is, instead of replacing them with placeholders. At this stage, only a subset of letters is handled, but it's a meaningful step forward in the program's development. This version demonstrates the benefits of working incrementally. You get to test small portions of logic in isolation, which helps ensure correctness and makes debugging easier. The code also includes a fix me comment, reminding the programmer to implement mappings for the remaining letters. By focusing on just one part of the mapping at a time, the program stays manageable and allows for quick feedback. This approach is especially useful when the logic involves many conditions or character cases, as it encourages thoughtful layering rather than overwhelming complexity all at once. The final version of the phone number program completes the letter-to-digit mapping for all characters from A to Z, treating them case-insensitively. This allows the user to enter a phone number like 1555 holiday or 1555 holiday, lowercase, and get the correct numeric output in either case. Digits and hyphens are retained, while letters are translated using a full mapping. The result is a complete and functional transformation program. What's especially important about this example is how it illustrates the power of incremental design. We saw how the program was built piece by piece, tested at each step, and eventually refined into a working product. This mirrors real-world software development practices, where complex features are rarely implemented all at once. Instead, they are gradually layered, verified, and adjusted as necessary. This final version not only demonstrates functional correctness, but also serves as a capstone example of good programming structure and process. The break statement is a control mechanism that allows you to exit a loop immediately, even if the loop condition hasn't yet become false. This is particularly useful when searching for a match or an early exit condition is met, saving unnecessary processing. The example in this slide involves nested loops that compute combinations of empanadas and tacos, checking whether their total cost equals the user's available budget. When a match is found, break exits the inner loop, and a condition in the outer loop can then terminate that as well. This simplifies the logic by avoiding more complex condition checks or flag variables. However, it's important to use break judiciously. While it can make code more efficient and responsive, overuse or misuse can lead to confusing control flow. When used thoughtfully, it offers a powerful way to improve both performance and clarity in loops that don't need to run to completion under every circumstance. The continue statement is another loop control tool, but instead of terminating the loop entirely, it skips the rest of the current iteration and jumps straight to the next one. This is useful when certain conditions should be excluded from further processing. The example provided deals with meal combinations for diners. The loop only wants to consider combinations where the total number of items is divisible evenly among diners. If that condition isn't met, a continue statement skips to the next combination without processing the rest of the loop body. This helps keep the loop body focused on valid cases, reducing unnecessary nesting and improving readability. Like break, continue should be used with care. It can simplify logic by short-circuiting bad cases early, but it can also make loops harder to follow if overused. In general, it's best used when a specific subset of inputs should be excluded from processing quickly and cleanly. Python offers a lesser-known feature, the else clause on loops. This construct runs only if the loop completes normally, meaning it didn't exit via break statement. It works with both while and for loops. In a while loop, the else clause executes when the condition becomes false. In a for loop, it runs when all items have been processed. If the loop exits prematurely via break, the else block is skipped. This structure allows you to distinguish between two different outcomes, completing all iterations versus exiting early. It can be especially useful in search tasks. For example, if you're scanning for a match and want to display a not found message only if the loop finishes without finding anything. The else clause adds semantic clarity, indicating that the loop ran its full course and no early exit occurred. Though not used frequently, it's a helpful tool for writing expressive and logically precise code. We continue with a concrete example of the for-else construct in action. The program prints a user-specified number of names from a predefined list. It uses a for loop with a break statement to exit early if the desired number of names has been printed. If the loop completes without encountering a break, that is, if the user asked for more names than are in the list, the else clause runs and prints a confirmation message saying all names. This pattern is useful for distinguishing between two types of loop exits, one due to a break and one due to natural completion. The for-else syntax makes this distinction explicit and removes the need for external flags or post-loop checks. It's especially valuable in search operations or controlled iterations, where follow-up behavior should differ based on whether a loop finished or exited early. This example shows how loop logic can be enhanced for clarity, allowing the structure of the code to clearly communicate intent. This slide introduces a common programming task, accessing both the index and the value of items during a loop. While this can be done using range of len combined with indexing, it requires extra code and can be less readable. In the example shown, the program uses range to loop through a list of numbers and manually accesses each element using its index. While this approach works, it's not ideal for readability or maintainability. It also introduces the risk of index errors, especially in more complex iterations. This pattern is often used by beginners, but it quickly becomes cumbersome in larger programs or nested loops. That's why Python provides a more elegant alternative, Enumerate, which we'll see on the next slide. Still, it's important to understand this manual method so you can recognize it in legacy code, or when working in lower-level languages that don't offer higher-level loop tools. Here we see Python's more efficient solution, the enumerate function. This built-in function simplifies the process of accessing both index and value during a loop. With enumerate, the loop automatically unpacks each index value pair, making the code cleaner and easier to read. In the example, enumerate is used to iterate through a list of numbers, and both the index and the value are printed on each loop iteration. This approach avoids the need for range of len and manual indexing. It also ensures that the correct index is paired with each value, even if the list contains duplicates. Additionally, enumerate uses Python's unpacking feature, where multiple variables can be assigned from a tuple-like structure. This leads to more expressive, Pythonic code that is both concise and self-explanatory. Understanding how to use enumerate is key to writing high-quality loop logic, especially when working with data structures that require position tracking alongside value processing. Finally, we will summarize the key concepts covered in the presentation. First, we saw that loops are essential for repetition, which is core to programming. We explored while loops, ideal for situations where the number of iterations is unknown, and for loops, which excel at iterating over known sequences or ranges. We then moved into loop control tools like break, continue, and the optional else clause that Python supports for both loop types. These tools give you more nuanced control over how and when loops execute. We also looked at enumerate, which provides a clean way to access index and value simultaneously during iteration. Finally, the idea of incremental development, writing and testing code in small steps, was emphasized as a critical practice for building robust and maintainable programs. Mastery of loops and related control structures gives you the ability to write powerful, flexible code that can solve a wide range of problems efficiently and clearly. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.